Hello everyone, welcome to Greenwave Academy, where we aim to make electronics easier and more accessible. In this video, we are going to explore how to build a smart data logger from scratch. This device can collect data from different types of sensors, process it, and transmit it wirelessly to a user interface for real-time monitoring or cloud storage. This kind of device has wide applications in fields like environmental monitoring, industrial data collection, smart homes, or even remote area monitoring. We will break down the architecture and features and show you how to design this system using a modular, scalable approach. So let's dive in it and take a look at how it all comes together. So what's the goal of this project? The aim is to build a smart data logger that can be used for a variety of applications. Technically speaking, the smart data logger is just a gateway for data. Think of it as a bridge that collects information from external sensors and logs it in real time. Whether you are monitoring the environment in an agriculture field, tracking air quality in smart home, or collecting industrial data from machines, this system is designed to be adaptable, flexible, and low power. It's built for real-time monitoring and handle multiple types of sensors and communication protocols, from Wi-Fi and Bluetooth for short-range connections to LoRaWAN for long-range communication. This data logger can scale to fit the need of almost any IoT project. The collected data is then transmitted to a cloud storage solution, where users can access and analyze it via a web interface from anywhere in the world. This kind of smart data logger can be used in several fields. For example, environmental monitoring, in agriculture or smart cities to track temperature and humidity and air quality, or also it can be used in industrial data logging for monitoring industrial systems and machinery using protocols like Modbus RTU. Also, for example, we can use it in remote area monitoring, as it is ideal for places where internet connectivity is limited but long-range communication is required, such as using LoRaWAN in agriculture, weather stations, or wildlife monitoring. Also, it can be used in smart homes or buildings for monitoring indoor air quality, temperature, or controlling HVAC systems, which here means heating, ventilation, and air conditioning. Now let's talk about the key features of our smart data logger that makes it versatile and suitable for wide range applications. First of all, we have multi-protocol sensor support, as it supports I2C, SPI, UART, and Modbus R2 communication protocols, allowing us to connect various environmental and industrial sensors both at 3.3 volt and 5 volt sensors are supported, which makes it compatible with a broader range of devices. The second feature is the wireless communication. The data logger is equipped with Wi-Fi, Bluetooth, and LoRaWAN communication capabilities. Wi-Fi and Bluetooth cover short-range communication, while LoRaWAN is perfect for long-range, low-power communication in remote areas. The third feature is the cloud connectivity, as all the data collected can be transmitted to the cloud for remote monitoring and storage when connected to internet. A user-friendly web interface allows access to real-time and historical data from anywhere. Also, we have low power consumption. This system is designed for low power consumption, which is crucial for battery-operated applications, especially in remote or hard-to-reach areas. Also, the design is modular and scalable, allowing us to add more sensors or upgrade communication modules based on the application. This flexibility makes it easier to adapt the system to different environments and project requirements. Before we dive into the specific hardware, let's look at the system architecture at a high level. We can break it down into three main sections. The input stage. This is where all the sensors come in. We will be using sensors that measure things like temperature, humidity, air quality, or anything else, depending on the project need. The system needs to be flexible enough to support different communication protocols such as I2C, SPI, UART, and Modbus RTU, so that we can connect both 3.3 volt and 5 volt sensors. The level shifter will handle the voltage difference to ensure seamless communication between the sensors and the processing unit. Now we'll move to the second part, which is processing unit. This is the heart of the system. It takes in all the sensor data processing and prepare it for transmission. Our processing unit needs to support multiple wireless communication protocols including Wi-Fi, Bluetooth, and LoRaWAN. It must also be low power to ensure battery life is extended for use in remote or low energy setting. The last section is communication and storage stage. Once the data is processed, it needs to be transmitted to the cloud for storage. Depending on the project requirements, we can use Wi-Fi or LoRaWAN for long-range transmission, while Bluetooth could be useful for short-range or mobile application. All of this data is then stored in the cloud, where it can be accessed through a user interface, giving users the ability to monitor real-time data or review historical trends. In this stage, we are discussing the general architecture without going into specific components like the microcontroller or communication chips, focusing only on the core system design. So now, let's dive into the hardware we will going to use to implement this architecture. The processing unit here, we are going to use the SPE32 LoRaWAN V3. This is our microcontroller which integrates Wi-Fi, Bluetooth, and LoRaWAN in one module. It's great for IoT projects because it supports multiple communication protocols and consumes very little power, which is crucial for battery-operated systems. This microcontroller will handle all the processing, communication, and data management. Now let's talk about the RS485, which is the Modbus interface. For our Modbus R2 sensors, we'll be using MAX 485 chips, which enables communication between industrial sensors and the microcontroller via the RS485 protocol. This makes the system industrial grade and capable of handling more rugged applications. Here we have the power supply. We'll be using lithium battery to ensure our device can run without constant power source. The ESP32 has low power mode, which means it can stay operational for extended period while consuming minimal power. Here we have the level shift. As we are dealing with both 3.3 volt and 5 volt sensors, a level shifter is needed to ensure smoother communication between components with different voltage levels. With these hardware components, we can create a robust system capable of collecting, processing, and transmitting sensor data efficiently. So there you have it. We have taken a look at how we can build a smart data logger from the system architecture to the hardware components that makes it all possible. This project is designed to be versatile and adaptable to different IoT applications, whether it is for environmental monitoring, industrial data logging, or remote area monitoring. In the next video, we'll start programming the sensors and setting up communication protocols. Make sure to subscribe to GreenWave Academy so you don't miss it, and visit our website at greenwaveacademy.com for more interesting projects. Thanks for watching, and let's keep making electronics easy.